Welcome to the Deep Dive. Today we're diving into something really interesting, how we teach and learn mathematics.
Yes, we've got this fascinating study. It looks at combining two approaches, flipped learning and realistic mathematics education, or RME.
Right, RME. The paper's title is, well, it's a bit of a mouthful. The Effect of Flipped Realistic Mathematics Education on Students' Achievement, Mathematics, Self-Efficacy, and Critical Thinking Tendency.
It is a dense title, yeah. But the core ideas could really, change things, make learning complex math maybe less of a solitary struggle.
Exactly. So if you've ever felt kind of overwhelmed by math concepts, this research looks at a method that might be more effective.
That's the idea. Our mission here is to unpack this combined approach. Let's call it F-RME, much simpler,
F-RME, good.
and see what the study says about how well it works. We're looking at student learning, their confidence, that's the self-efficacy bit, and critical thinking.
Okay, so think of this as your quick guide to a potentially, well, groundbreaking way to learn math. The study itself involved first-year pre-engineering students.
That's right, in Ethiopia. And they compared this F-RME group to another group using a conventional RME.
Now, you mentioned it's quasi-experimental because they couldn't randomize the students.
Exactly. That's a crucial point. It means we can't be absolutely certain the groups were perfectly matched at the start.
So we need to be a little cautious when we interpret the results.
A little, yes. Though the researchers did try to account for any initial differences statistically, it's still valuable data, just, with that caveat.
Got it. Okay, so let's get down to basics. What exactly are flipped learning and RME on their own?
Okay, flipped learning first.
Yeah.
The core idea, and folks like Bergman and Sams really pushed this, is shifting the initial exposure to new stuff outside the classroom.
So like watching videos or reading at home?
Precisely. Then class time is freed up for more interactive things, applying concepts, deeper understanding, working together, getting help from the instructor.
Right, so it caters more to individual speeds, maybe? And boosts interaction.
That's the goal. The out-of-class part is really about building a basic understanding, a foundation.
Okay.
So everyone's ready for the in-class activities. And it's really key that those two parts, pre-class and in-class, are aligned. They have to build on each other.
Makes sense. So you get the basics down first, then you dive deeper in class. Now, realistic mathematics education, RME, that sounds specific. Where did it come from?
It did, yeah. It came from the Freudenthal Institute in the Netherlands. The founder, Hans Freudenthal, his big idea was that math should be grounded in reality.
Reality, like real-world problems.
Yes, but not only that, it's about math as a human activity. So reality can be the everyday world, or it could even be the formal world of mathematics itself, as long as the learner sees it as real, as meaningful.
Ah, okay, so it feels less abstract.
Exactly. And another key person, Lean Streefland, stressed that students need to be able to visualize scenarios, engage in activities they find worthwhile. It's about making math feel relevant.
Okay, I see the connection now. Both flipped learning and RME seem to shift focus, away from the teacher just lecturing.
Absolutely. They both move towards a more student-centered classroom. RME's emphasis on active participation, collaboration, it fits perfectly with the in-class part of flipped learning.
So class time isn't passive listening anymore.
Right. It's about investigating higher-level thinking, doing mathematics, as one researcher, Fauzan, put it. It means tackling contextual problems interactively.
And this RME approach, it's been used before.
Oh, yes. Successfully used for lots of topic sequence. Probability, calculus, geometry. There's good work by people like Gravemeijer and Dorman on using it for calculus, for instance.
So combining these two, F-RME,
Oh.
why did the researchers feel this specific combination was needed? Was there a gap?
There was. They pointed out a couple of things. First, lots of flipped classroom studies look at test scores, but they don't always examine the learning theories behind how the flipped activities are designed.
Ah, okay. The why it works, not just if it works.
Kind of, yeah. And second, most research was from the US and China. Less was known about how well it works in, say, developing countries.
Like Ethiopia, in this case.
Yeah, exactly. So this study aimed to tackle both. Combine flip learning with a solid theory, RME, and test it in a different context. They thought the flipped video prep could actually make RME more practical for teachers, helping them cover content meaningfully without sacrificing the RME principles.
That makes a lot of sense. Okay, so the study set out to answer specific questions about F-RME.
Yes, three main ones. First, does F-RME impact learning achievement differently than conventional RME?
Okay, learning outcomes.
Second, What about mathematics self-efficacy? Does F-RME affect students' confidence in their math abilities differently?
Confidence, right.
And third, critical thinking tendency. Is there a difference in how the two approaches influence students' inclination to think critically?
Achievement, confidence, critical thinking. Got it. Now, how do they actually implement RME principles within this flipped setup? You mentioned there were core principles.
Yes, scholars like Van den Heuvel-Panhuisen and Drivers identified 6 key RME principles, and this study deliberately wove them into the F-RME design.
Okay, what's the first one?
The activity principle. Students need to be active builders of their own knowledge. In F-RME, this happened through the pre-class video tasks and the in-class group work.
Active learning. Makes sense.
Then the interactivity principle. Learning is social, collaboration, and discussion are key. This was central to the in-class group discussions in F-RME.
So, talking it through with others.
Exactly. Third is the reality principle, which we touched on, using real-world, visualizable, meaningful scenarios.
Like the speeding ticket example for the mean value theorem they mentioned.
Precisely that kind of thing, used in the pre-class activities to set the stage. Fourth is the level principle.
Level principle.
Yeah, it's about progressing through levels of understanding, starting maybe with informal, situational thinking, and gradually moving towards more formal mathematical language and symbols.
Like going from sharing pizza to adding fractions formally.
That's a great analogy, yes. The F-RME approach encouraged starting with informal solutions to real problems, then guiding students to develop the formal math from there.
Building from concrete to abstract.
Yeah.
Okay. What else?
Fifth is the intertwinement principle. Math topics aren't isolated islands, they're connected. The pre-class problems were often designed to require knowledge from different areas like coordinate geometry, calculus, maybe even physics, all intertwined.
So making connections across topics.
Right. And finally, the guidance principle. This is about guided reinvention. The teacher facilitates, guides, but doesn't just give answers. Students kind of rediscover mathematical ideas with support.
So the teacher is more of a guide than a lecturer in the classroom part.
Exactly. Implemented during those in-class group activities. The study actually has a table showing how each principle linked to specific pre-class and in-class activities.
Sounds very structured. So what did this F-RME classroom actually look like for a student?
Okay, so before class, watch the videos, maybe read some notes, do embedded quizzes in the videos. They used Edpuzzle for that.
Edpuzzle,
Oh, okay.
right? The tool that lets you put questions right into the video.
Exactly. So students get immediate feedback, and the instructor can see who's watched, who's struggling. They also got the RME-style real-world problem to think about beforehand. All this was managed through Google Classroom notes, links, quizzes, problems, all there.
So technology was pretty central to managing the pre-class part.
Definitely. Edpuzzle for the interactive videos, Google Classroom as the hub.
And then in class.
In class, it started with clarifying any confusion from the pre-class work. Then into groups to discuss the real-world problem, figure out how to solve it, try their method, get feedback.
From the instructor and peers.
Yes. Then they'd work on generalizing their solution, maybe develop a formula or model. And then this is cool. Each group prepared a short, like 5-7-minute presentation on their findings.
Oh, wow. So they had to articulate their thinking.
Right. Followed by a whole class discussion and reflection. It sounds very active.
It really does. Okay, so that's the F-RME setup. How did they actually run the experiment over the 3 weeks?
Okay, week 1 was set up. Introducing F-RME to the experimental group. The rationale, benefits, challenges, syllabus, how to use the tech. A basic session on derivatives. And importantly, pre-tests and pre-questionnaires for both groups.
Baseline measures. Got it. Then week 2 was the intervention.
Week 2 was go time. The F-RME group did the pre-class videos, quizzes, problem-thinking routine we just described. In class, clarification, group work, presentations, discussion. Topics covered things like finding max-min of functions, mean value theorem, inflection points, related rates, all applications of derivatives.
And the control group, what were they doing in week 2?
They were the conventional RME group, or CRME. They were told to look over the learning materials outside class. Then in class, they got a lecture on basic concepts first, then did RME-based learning activities.
So still RME, but without the structured pre-class video learning and problem intro.
Exactly. Same instructor, same content, same total class time, 4 hours over the topics. The key difference was how that time and the out-of-class prep were structured.
Okay, and week 3?
Week 3 was wrap-up and assessment. Post-tests and post-questionnaires for both groups. Plus, those interviews with 4 randomly chosen students from the F-RME group, about 20 minutes each.
Right, to get the qualitative perspective. So let's talk about the measurement tools. The tests.
The pre-test and post-test were developed by the researcher who had over 10 years of experience. Pre-test had true-false, multiple choice. Post-test was all multiple choice, covering calculations and concepts. Content validity was checked by 2 assistant professors.
Okay. And reliability.
They checked the post-test's internal consistency using Cronbach's alpha. It was 0.79, which is considered good.
Solid. What about the questionnaires for self-efficacy and critical thinking?
For math self-efficacy, they adapted items from a standard tool, the MSLQ. 5 items, 5-point Likert scale, like I'm confident I can understand the basic concepts. Reliability in this study was high, alpha 0.86.
Very good. And critical thinking.
That was adapted from work by Chai and colleagues. 3 items, 5-point scale example. I will try to understand new information from different viewpoints. Original alpha was 0.71, also considered acceptable.
And the interviews were semi-structured, asking about their experience, what they liked, benefits, sense of control.
Exactly. Then they analyze the interview responses for common themes. So a mix of quantitative scores and qualitative insights.
Okay, the moment of truth. What do they find? Did F-RME make a difference?
Well, first off, both groups significantly improved their learning achievement from pre-test to post-test. That suggests RME itself, in either form, is helpful.
Okay, good baseline. But the comparison.
Here's the key finding. The F-RME group scored significantly higher on the post-test than the conventional RME group. The statistical analysis, Ankovi, confirmed this, and the effect size was medium to large.
Wow. Significantly higher achievement. That's big.
It really is. It suggests that specific F-RME structure added something important.
What about confidence? The self-efficacy part.
Similar story. The F-RME group showed a significant increase in their math self-efficacy from pre to post questionnaire. The CRME group's increase wasn't statistically significant.
Interesting. So F-RME boosted confidence more.
And not just the increase of the F-RME group also ended up with significantly higher self-efficacy scores overall on the post-questionnaire compared to the CRME group. Again, medium to large effect size.
Higher achievement and higher confidence. That's a powerful combo. And critical thinking tendency.
Here, both groups showed significant improvement over time, so both methods seem to foster critical thinking tendencies.
Okay.
However, just like the other measures, the F-RME group scored significantly higher on the critical thinking post-questionnaire than the CRME group. Effect size was medium to large again.
So across all 3, achievement, self-efficacy, critical thinking tendency, F-RME came out ahead significantly.
That's what the quantitative data suggests, yes.
What did the student interviews add? Did they shed light on why F-RME might be working so well?
They really did. 3 main themes emerged. First, F-RME promotes collaboration and interaction. Students felt that learning basics at home freed up class time for valuable discussion with peers and the teacher.
Like getting more personalized feedback and time to work together.
Exactly. One student contrasted it with traditional lectures where there wasn't much chance to share ideas. They felt the F-RME group discussions and presentations really helped them perform better.
That highlights the value of that active in-class time. What were the other themes?
Second theme, F-RME allows personalized learning. Students love being able to control the video pace, pause, rewind, rewatch.
Right. Learn at their own speed.
They felt it helped them get a deeper understanding. Third theme, F-RME promotes problem-solving ability. Dealing with those real-world problems pre-class apparently made it easier to visualize and start thinking about solutions.
So the context helped. Made it more engaging.
It seems so. One student said learning basics beforehand meant more time for deep classroom discussion, which helped them think more creatively.
So the students' experiences really seemed to back up the quantitative findings. What were the researchers' main conclusions then? How did they interpret all this?
They concluded that, yes, F-RME appears to be an effective way to improve achievement, self-efficacy, and critical thinking tendency in this context. They suggested the pre-class work provides that crucial foundation.
Setting students up for success in class.
Right, and they linked this to other research suggesting that self-paced learning and videos can reduce cognitive load and improve understanding. Moving the RME real-world problems to pre-class also seemed key, giving students time to explore independently before the group work.
So that structure really mattered. What about the boost in confidence and critical thinking?
They figure the increased active learning opportunities in F-RME likely boost self-efficacy. Succeeding breeds confidence, which aligns with Bandura's social cognitive theory. Prior knowledge from pre-class work likely helps too.
Makes sense. If you feel prepared, you participate more, you succeed more.
Exactly. And for critical thinking, they argue that engaging with realistic contexts and thinking deeply about them, as F-RME encourages, positively impacts that tendency. Contextual learning helps you understand better and use different strategies.
Okay, so it seems like a really promising approach. Did they offer practical tips for teachers who might want to try F-RME?
We did some practical steps. First, select content suitable for flipping. Second, find relevant real-world contexts, ideally ones that connect different math ideas.
So thoughtful design up front.
Very much so. Third, prepare the materials carefully, videos for home, activities for class. Fourth, be ready to facilitate that collaborative group work effectively.
Guide on the side, not sage on the stage.
Precisely.
No.
And fifth, use user-friendly tech platforms to manage it all, sharing videos, tracking quizzes, etc.
That's helpful advice. Did they mention any limitations of this study or areas for future research?
Yes, definitely. One potential limitation is the novelty effect. Maybe the F-RME group was just excited about doing something new.
Ah, the Hawthorne effect kind of idea.
Something like that. So they suggest longer-term studies, maybe with delayed post-tests, to see if the benefits stick around.
Good point. Anything else?
They also noted that critical thinking was measured as a tendency via self-report, not ability via a direct test. So future research could use ability-based tests and, again, look long-term.
Measuring the skill itself, not just the inclination.
Right. And finally, the sample was specific pre-engineering students in southern Ethiopia. So generalizing these findings to other students, other places, other subjects, we need to be cautious.
Fair enough. Limitations are important to keep in mind. But
Overall, despite those limitations, it provides pretty compelling evidence for this F-RME approach. It seems to genuinely enhance not just learning, but also confidence and critical thinking.
okay, so let's wrap up this deep dive. We've looked at how combining flipped learning with realistic mathematics education, F-RME, seems to really boost student outcomes in math.
Yeah, the study showed significant improvements in achievement, math, self-efficacy, and critical thinking tendency for the F-RME group compared to conventional RME.
And it seems that engaging with those real-world problems before class, coupled with active collaborative learning in class, were key ingredients.
Absolutely. Which leads to maybe a final thought for you listening. Even outside a formal classroom, how could you incorporate more real-world relevance and active learning into how you approach new information?
That's interesting. Like, how could grounding something in a real context first or actively trying to apply it change how you learn?
Exactly. Think about how getting those foundational concepts down beforehand might unlock deeper engagement and better problem solving when you tackle something complex.
Definitely something to mull over.
Yeah.
If you want to dig deeper, you could explore realistic mathematics education principles or just the broader research on flipped learning. Applying these ideas might just spark new ways to learn in your own field. Thanks for joining us for this deep dive.